So for the last two class for the module 3 we have seen about economic dispatch problem by neglecting the losses, or we are not included the losses. So now but in practical it is not possible, because for entire Karnataka we don't have a single power plant. The power plant is shifted, or it is having many power plants, or it is distributed, not centralized. If that is the case, then say if the load is shared between two power plants, then definitely obviously there will be some transmission losses. So we in practical we can't able to eliminate the losses, we need to include the losses, then only the economic dispatch problem will be more realistic, or it is acceptable. So if there are more power plants or different power plants located at different places, then power losses cannot be ignored, and this power loss taking place, this PL, we will call this as PL, power loss will be around 5% to 15%. So we need to definitely include this power loss, then only we can tell the optimization or the economic dispatch problem is more practical in nature. If that is the case, we know that we already know without including or not including the losses, we know the objective function is to minimize the cost, and this is nothing but the summation of I is equal to 1 to n and Ci Pgi. So the cost for the each and every generators, if you do the summation for all, then we will get the total cost, and we need to minimize this total cost. But here the constraint is little bit different. So last time the constraint is like this: the total power generated must be equal to the demand, the total demand or demand. But this is not the case if you are including the loss. If you are including the loss, then the total power generated should be equal to the demand plus the loss, plus the total loss. In general we can write Pg is equal to Pd plus PL. If you make this as the equality constraint, then I will write like this, the power flow equation like this: Pg, the summation of all the power generated, minus Pd minus PL is equal to 0. So this will be the equality constraints. We need to maintain this constraint, and also to achieve this objective function of the minimization. As we already know that we are using the Lagrangian method to solve this type of problem statement, the same Lagrangian method we need to give for including these constraints. We know that the Lagrangian function L is nothing but the augmented function of the objective function as well as the constraints. So if that is the case, the same Lagrangian method or Lagrangian equation or augmented equation will be taken the original objective function of the cost, it's nothing but Ci Pgi minus lambda of this G. So G is nothing but the constraints. So here G is nothing but the constraints. So I will take this G inside. It's nothing but lambda I is equal to 1 to n, and then this is Pgi minus Pd minus PL. So this is the augmented function we got here, and this PL is the part of, if you see, this Pd is not depending upon our generator. The Pd is nothing but the demand, which is nothing related to our generator, but this generation is related to this Pg because of the constraint, but this Pd is independent. So whatever the demand required by the consumer is independent of the power generator, but this power generation should be a part of this Pd, or otherwise this loss is not be given by the consumer, but this loss is due to this generation. If there is no generation, there is no loss, right? So if there is a loss because of the generation only, so this PL is a part of this Pg. So while differentiating this Lagrangian equation or the augmented equation with respect to Pg, we can eliminate this Pd, but we should not eliminate this PL, because this PL is the part of Pg. That you need to take care, or you need to understand that concept. So next step is, as usual, as per the Lagrangian method, we need to differentiate that augmented equation d L with respect to the power generated. If that is the case, then I will get this. I will get the differentiate of this one, and then I may get the differentiate of Pg, and also I need to take care of PL, because we know that PL is also a part. So this lambda will have 1, this is constant, then it will become as 1, and we need to differentiate this PL, and also we need to differentiate this cost. So this will become, after differentiating, dCi divided by dPgi, and then this is the constant, so it is 1, so it will have minus lambda of this 1 minus, this will be 0 because it's not depend upon this Pgi, but it is depend, so I need to differentiate this PL divided by dPgi. So this will be your what, dL divided by dPgi. So this is nothing but, so if I take into the same thing into the next page, I will get dCi divided by dPgi minus lambda over 1 minus dPL divided by dPgi. So this is my partial differentiation of this Lagrangian equation with respect to the power generator. And if you calculate the lambda from this equation, then the lambda will be, lambda is equal to, and this part will go to here it will come 1 minus dPL divided by dPgi, and then this part will come here, dCi divided by dPgi. So this will be my lambda value. And we know that by seeing this equation, what you have observed, this is nothing but the incremental cost. If you differentiate the cost with the generation, then this is nothing but the incremental cost. What is that? Incremental cost, IC. If you recall, if you go back and check, we differentiate this cost with respect to this, and we call this equation as the incremental cost. And in general, the penalty factor, we will call penalty factor, PF is nothing but 1 divided by 1 minus dPL divided by dPgi. So this is called the penalty factor. So we know what is IC and we know penalty factor, and if you look this is the penalty factor. So this is the incremental cost and this is the penalty factor. So this lambda can be easily calculated with two things. One is called the incremental cost of this I, and also penalty factor. This penalty factor can be written as Li. So Li is nothing but the penalty factor. So I will call this as Li. So this is to find the lambda. So if you know the incremental cost and if you know the penalty factor, then we will find out the lambda. So we all know that the lambda is playing an important role to get the optimization value. Even for not including the losses, we find out that lambda is very, very important. So you need to understand this concept. And also, if you see this PL means dPL divided by dPgi is nothing but incremental transmission loss. So one more term I am telling, that incremental transmission loss. So they will write this as ITL. So this incremental transmission loss is nothing but dPL divided by dPgi. So you can replace this term with ITL, so you should not get confused. In some textbook they will give directly as ITCL. ITCL is nothing but incremental transmission loss. So this is nothing but, if you differentiate the loss with respect to the generator, you will get incremental transmission loss. If you differentiate the cost with respect to the power generator, you will get incremental cost. And if you are having this type of equation, 1 divided by 1 minus this incremental transmission loss, then this is called penalty factor. So these terms you need to be memorized, or you need to be understand at any time of the optimization allocation of the generator. These terms you should be memorized, or you need to understand clearly what is going on there. Okay, with this input we will start derive optimum allocation of the generator. So we'll call So these are all the basic idea about including the losses. So when you include the loss, these are all the terminology we are getting. So you need to take care about this, or you need to understand about this. And then we will go for optimum allocation of the generator. Now actually we are coming to our problem. The previous two slides are just to understand the concepts. What will happen if losses is included? Now I need to allocate the generator such a way that by including the losses. So by considering Bij coefficient, I will tell what is this Bij. This is J. Bij I will tell, don't worry. Our aim is to optimize the allocation of generator by including the losses. So once again I am telling, if you are considering two bus system. Why? Because loss will occur one and only if the generators are different, feeding to the different buses. So maybe this will be generator 1, and there is a generator between here, this is generator 2, and there is a transmission line connected to this, and you may get a demand also here. I will call this demand as PD1, and you may have a demand here also, PD2. So obviously, say for example, if total demand is summation of the demands and then total generation is summation of these generators, and I need to satisfy this two generator, the power produced by these two generator must be equal to the summation of the demand required. But there are some losses in this transmission line, we need to include that also. That is what we have seen in the last two slides, right? Then we need to consider, or we need to plan accordingly, what will be our PL or transmission line. I will call this as the transmission loss, PL. So this transmission loss is nothing but all summation of I is equal to J of N, and then the summation of, this I is equal to 1, this is numerical 1 and this is character 1, I is equal to 1 to N, and this is J is equal to 1 to N, and then power generated of this ith generator, because I will call this as I will call this as J. So this power generated because of this I, and then new term I included Bij. I will come to Bij later, but you understand, I taken the generator I, also I am taken the generator J, and this Bij, I will write here, this Bij is the loss formula, because I am not only producing the generator and also I am creating some losses. Because of the generation there are some losses. So Bij is the loss formula coefficient matrix. So this is the loss coefficient matrix, loss formula coefficient matrix. Okay. So next we need to think about, so we have taken two bus systems, say this is bus number 1, then this is bus number 2. So I'll go for a new slide. So therefore we need to find out the losses for two bus systems. So for two bus system, this PL can be expand as PL is equal to summation of I is equal to 1 to 2, and then this is I, and this is J is equal to 1 to 2, because there are two. So I need to consider for two things, because this this generator will have loss from here to there and as well as from there to here. So both side this will produce losses, and also these two also will give both side the losses. I need to consider I1 to 2, J1 to 2, and also this is BGI, PGI, and then BIJ, and this is PGJ. So I need to expand this this equation. So how I can do? Let me take first this and then I will come up to this. So if I take inside, then it will be I is equal to 1 to 2, and then so J is equal to 1 to 2 means wherever I am getting J, I need to add the summation of 2 times. So I will take this PG outside. So PGI I taken outside. Wherever I am getting PIJ, I need to add this. So I will get P I took outside, so only I will get these two terms. So B I 1 and then PG 1 plus wherever I am getting J, I need to add 1 2. So again B I 2 and then PG 2. So this will be this summation is over now. Because of this, this summation is over. One more outer summation is there, and if I take that, wherever I am getting I need to replace with 1 and then 2, right? So just a summation. So PG1 B11 PG1 plus B12 PG2, and then for second term PG2 B12 PG1 plus B22 PG2. Okay, and then still if I multiply and substitute the PIG1 inside and PG2 inside, I will get PL is equal to PG1 square B11 plus B12 and PG1 PG2 plus B12 PG1 PG2 plus B22 PG2 square. So I will get PL like this. Here one thing I need to understand is B12 is equal to B21 because this is a symmetrical matrix. Both are symmetrical matrix. It's because of that B12 is equal to B21. If I am taking that that as an account, then I will get the total PL is equal to PG1 square B11 plus 2 into B12 PG1 PG2 plus B22 PG2 square. So I will come with this equation. So this is one form of PL. So I'll get the PL means the transmission loss through by solving this equation, or in short I can convert it in the matrix form like this. In short, this PL will be in matrix form PG1 PG2 with the with 2 bus system, right? So B11 B12 and this is B21 and this is B22, and also PG1 PG2. So by solving this we will get, if you see this and these are transpose, both are transpose. If that is the case, I will still write in simple this PL is equal to PG transpose Bij and then PG. So I will write a generalized equation for this. PL is equal to PG transpose Bij PG. Okay, then just a minute. Then I am going for the cost function. So power transmission losses we got. So how the cost function will be there for including losses? So cost function for 2 bus system. Only we are considering for 2 bus systems. So C1 is equal to C1 PG1 square plus B1 G1 plus A1, I mean that is PG1 A1, and then C2 is equal to C2. So this C is different, this C is different, this is cost and this is constant we are getting from the graph, that is heat rate curve graph we are getting C, no, that C this is, so don't get confused. And then PG2 square plus B2 PG2 plus A2. So this is the cost function for 2 bus system. And then if you see the incremental cost, so what is incremental cost? IC. So IC 1 is equal to, if you differentiate the cost equation with respect to power generator of this G1, then I will get, so if I differentiate this, I will get the remaining thing is 2C1 PG1 plus B1 I will get. And then if I differentiate this cost, incremental cost equation is nothing but differentiating this cost equation 2 with respect to the power generated of the second generator, then I will get, so 2C2 PG2 plus B2. So these are all the incremental cost and this is the cost function. So we come up with all the basics whichever we need for this. And then if I apply this value we got from this PL, okay. So next we are going to see about one more term, missing term. What terms we are missing? Something we are missing like this. So we got this, what is it? We got this, we got the cost, normal cost and incremental cost we get, but we need to find out the incremental transmission loss, that is nothing but ITCL. We will get this by differentiating the loss equation with respect to the generator. So where is loss equation here? So the loss equation is here. So if you differentiate this equation with respect to the generator, so that I will call as incremental transmission loss. So incremental transmission loss, that is ITL1. This is nothing but differentiate the power loss equation with respect to PG1, and I will get, if you differentiate that, I will get 2B11 PG1 plus B12 PG2. So I will get this. If you differentiate that equation PL with respect to, you will get this. You can solve also, no problem. And then ITL2 is nothing but differentiate the same equation with the PG2, then I will get 2B22 PG2 plus B12 PG1. So I will get this equation. And we all know that what is the condition for optimum operation is the lambda for generator 1 must be equal to lambda of generator 2. So this is the condition for optimum operation. So what is the optimum operation for us? To minimize the cost. So to minimize the cost, the condition is lambda 1 is equal to lambda 2. This is the condition. While writing algorithm, these things you should remind. That is why we are deriving in detail. Okay, so these are all the things we need to find out. And we all know that lambda is nothing but IC multiplication of ICI multiplication of lambda for all lambda I. This is the generalized equation just we derived now. And one more thing, we know that this Li is what? Just recall. So this Li is nothing but this value, that is nothing but Li is nothing but the penalty factor. So this is the penalty factor and this is incremental cost. If you know these two things, then lambda is find out. And what is the optimum operation condition? This lambda must be lambda 1 is equal to lambda 2 for our 2 bus condition. For 3 bus condition, up to n, it should be up to n, all must be equal, then only it is operating at the minimum. Our objective function is achieved, otherwise it's not. Then we all know that this penalty factor Li is nothing but penalty factor, and this is nothing but 1 divided by 1 minus ITL of I. So penalty factor. So from this equation we know what is ITL. So ITL1 is nothing but this. So apply this, and then IC also we know what is IC. IC also we got here. Just apply this two value for this lambda. So if you apply this value for this lambda, that is nothing but lambda 1 is equal to lambda 2. So for lambda 1 we know the formulas. Just by applying the formula I will get 2CI1 PG1 plus B1 whole divided by 1 minus 2 B11 PG1 plus B12 PG2. So this is for lambda 1 is equal to lambda 2. Lambda 2 is nothing but 2C2 PG2 plus B2 whole divided by 1 minus 2 B22 PG2 plus B12 PG1. So this is nothing but just we applied all the values of this penalty factor and the incremental cost. So penalty factor is this value, and then incremental cost is this value. Just by applying that to our lambda formula we will get this. And one more condition, this is also very important constraints you need to take care. I will mark this as equation, maybe equation 1 for our solving for this type. And then we know the equality constraint. What is the equality constraint? This is one constraint, constraint 1, and one more constraint is equality constraint. So equality constraint is nothing but the power balance equation. So power balance equation is nothing but the power generated for the for all the generator 1 to 2 bus system, and then PGI must be equal to PD plus PL, means the demand required plus the losses. If these two summation of these two is equal to the power generated, then it is satisfied, right? So we are getting two generators here, so I will write here PG1 plus PG2 must be equal to the demand required and this PL. What is PL equation? PL equation is here. So this is the PL equation. So if I write this PL equation here, then I will get B11 PG1 square plus 2 PG1 B12 PG2 plus B22 PG2 whole square. So I will call this as equation 2. Then if you solve this two equation, then definitely we will get a value of PG1 and then PG2. So this PG1 and PG2 is the optimum condition. So this is nothing but optimum value. So by solving this equation 1 and equation 2, we will get with the result of PG1 and PG2, and if you allocate the load by the values you get from this PG1 and PG2, then that is the optimum condition. Understand? So this optimum condition is satisfying this and this. So we are getting this value. Any doubt about this? Any doubt?
No, sir.
It's clear, right?
Yes.
Okay. Next, we need to find PGI in a systematic way. So in last class also, in last in without classes also, we concluded how to find out. So these are all the very big steps, right? Very what complicated. So by considering the lambda and also by considering all these constraints, we need to come up with what systematic way, or it should be solved in hand. So how to find out that? So to another in to solve in practical or in the calculation, so to find PGI, okay, so I will consider this incremental cost is nothing but 2CIPG plus BI. So this is the incremental cost, we all know. And then PL in generalized way I will write I is equal to 1 to n, j is equal to 1 to n, PGI, BIJ, and then this is PGJ. Now I know that this incremental cost is nothing but, if I differentiate this PL with respect to dPGI, I will get, after differentiation of this PL, I will get the summation of j is equal to 1 to n. So the left out is 2Bij PGI. You can solve after differentiate, I will get this only. You can solve this by going back the upper slides. I am writing the final values directly. So this is my differentiation of losses with respect to dPij. So what is this? How we can call this as? If you differentiate the loss with respect to power generated, what is the name for that? Can you recall? What is this? Incremental. What is this? My incremental transmission loss. So this is nothing but the incremental transmission loss. Okay, and then we know the coordinating equation. Coordination equation is nothing but IC. Coordinating equation I must be equal to the value of 1 minus ITC. This also we derived. If that is the case, we know what is IC, incremental cost value. Then substitute that value. I will come up with 2CI PGI plus BI is nothing but the incremental cost is equal to lambda, and just apply that incremental transmission loss, that is nothing but 1 minus summation of j is equal to 1 to n, and then 2 Bij PGI. This is nothing but, this part is nothing but incremental transmission loss. So by solving this 2CI PGI plus BI is equal to what I will do is I will separate all the ith element from this summation. So if I removing all the ith element, then I will get minus lambda 2 Bij means I will get, because I need to remove all the I items from outside, and then I will get PGI. So if I remove all the ith element from this summation, and the left out is minus lambda summation of I is equal to 1, and I is definitely not is equal to, sorry, this is j, right? J is equal to 1 and j is definitely not equal to I, and then it will go up to n, and 2 Bij PGI. I will get this as the remaining. So this is equal, and this is lambda minus, I removed all the ith element, so this is nothing but ith element from this summation. So the left out is given here. If that is the case, I want to separate all the PG. because my aim is to find out the PG only, so I removing all the PGs outside from this entire equation. So I will get 2Ci plus 2 lambda BII is equal to lambda minus BI minus lambda j is equal to 1 and j is not equal to I over n 2 Bij PG PGJ. This is, yes, because PGJ here also this J, PGJ. And if I take PG this side and everything the left hand side, then I will get PGI is equal to 1 minus BI by lambda minus summation of j is equal to 1 and j is not equal to I over n, and this is 2 Bij PGI whole divided by 2 Ci by lambda plus 2 Bij. Sorry, this is 2 Bii. Sorry, this is 2 Bii, because that side this part will come now. So ith element. So we are on Bii. Please change. This is Bii. So this is very important. For entire problem, you are going to solve this equation only. So if you solve all these values, all these lambda values, and if you are getting some value of this generator, then that value is the optimized value, we can tell. So in last 3 or 4 problems, we solved lambda for every step. We know what is the formula for lambda, we by hearted. Like that, you need to by heart this formula. Very important. Up to this, what we have seen, how we derived this PIG is what we have seen from around 6 to 7 slides. So you know all the terminologies we are going to use in this formula. We know all the each and every formulas. So if you know this formula, finally if you know this formula, and then if you substitute all the values inside this formula, then you will get the answer. But there is a procedure to get this PIG. That procedure I will take in next class. That is called algorithm. So algorithm to find out the optimum dispatch, including the losses, how we can give, that we will see in the next class. Up to this, any doubt? Up to this, if you have any doubt, we can discuss.